Hi, welcome back. In this lecture I will introduce MPI data types. It turns out that MPI data types are one of the most difficult concepts in MPI. So the goal of my lecture today is to give you a big, broad overview of MPI data types concepts and tell you, where it's typically used and what are the advantages. I will let you then to look at more in details in the textbook to see how technically use this in application. But I want to basically follow me, understand what are the major motivation for using data types in MPI. So in application, one of the most common communication patterns is the so-called halo exchange, also called a ghost cell exchange. The typical HPC application consists of a big grid, and this big grid is divided among many small grids. Each one of these grids is assigned to an MPI process. So let's look at an example here. So we have a big grid that has been divided in 12 different smaller grids. Each of these smaller grids is the small square here, and is basically assigned to one process. So in this case, we have 12 processes and 12 small grids. If we put together all these 12 grids, we get back to the original big grid. So in most of the PDE calculations required to calculate derivative, right? So the derivative, in order to calculate derivative, we will need at the very least 3 points in 1D. We will need the values on one point, the values on the right, and then the values on the left grid points, right? So what happens here on the grid points here on this left, on the left grid points here on this edge here. So all these points, they require the values defined on this edge, the values defined on the right edge. But also we need the values that have been defined on a different grid on a different process, right? So in order to get this, we basically need to communicate. We need to communicate what are these value here on this edge to here, right? We typically place on a so-called ghost cell. So we make an additional edge here, and then we move the values from this column here to the ghost cell that we have here. On the same way, this column here needs the values that are basically here. So we need to communicate this value here from this process to this process here, right? So at each time step, before actually calculating the derivative, we need to swap in this case, the first column here with the last column here, right, in order to calculate the derivative. So this pattern is called halo exchange, and is very common in all application. So how we do this? Well, we basically have loops between 0 and the number of neighbors, and then we basically do first the MPI send. So we send in one direction. We basically provide the starting address of our edge. In this case, is our column, right? And we provide what is the site. On the same time, also we need to post a receive through all the neighbors to enable this holo exchange. So when we have the data organized in our subgrid, some of the data will be contiguous in memory, but other data will be not contiguous, right? So there will be a stride. So if we have a two-dimensional array storing the data for our two-dimensional grid, some data can be sent continuously, but some data we will basically need to send with a stride. So in fact, for all but one decomposition, some data is continuous, others is actually strided. So one possible usage of MPI data types is have a continuous data representation of strided memory access. So how we do the hollow exchange? Well, the most common approach that pretty much all the application developers use is actually to do something like this. We make a temporary buffer, right? And then we copy our data. In this case is a strided access on our array, and then we basically save it in this temporary array, and then we use MPI send and receive using these temporary arrays. So one of the problems this is actually the performance. So the MPI implementation on the top of this extra copy to this user buffer, they might need to copy the data from the buffer to a special memory, that is the internal MPI buffer for sending and receiving. Right. Of course, this depends on many details of the MPI implementation and on the interconnect design. But we saw in the previous lecture that we use extra buffers. MPI use extra buffers for the communication. So MPI provides a neat way to efficiently and concisely define non-continuous patterns in memory via MPI data types. So MPI implementation might be able to avoid one memory copy by using this description as MPI data types. So MPI, so as we saw in MPI send, receive, the data in a message to be sent or received is described by a triplet consisting of the starting address, the count, and the data type. So today we focus on this data type. At the moment we just use a primitive data type, so MPI int, MPI float, MPI double. We can actually define our own MPI data type. So how we do that? Well, the way to define that is recursively defining as predefined corresponding to a data type from the language. So we can use MPI int, MPI double, MPI float. We can define a continuous array of MPI data types. We can define a strided block of data types. That's a particular case that we are looking at today. We can use an index array of blocks of data types, and also we can use an arbitrary structure of data types. There are MPI functions to construct custom or derived data types. So for instance, an array of int or pairs, or also a row or a column of the matrix. So why we want to use data types? Since all the data is labeled by a type, an MPI implementation can support communication between processes on machine with the very different memory representation and lengths of elementary data types. This is called heterogeneous communication. So one typical case is for instance, the representation of an integer on different machine. In some machine can be 4 bytes, in some machine can be 2 bytes, right? So how we handle the problem of communicating an integer that might have different length on different system. So let's say that I want to send an integer from a machine using 4 bytes to a machine using 2 bytes, right? So the MPI solved this problem by defining a data types that might have a different size on the two different machines. By using MPI int, we will know that on certain machine MPI will be 2 byte long, in another machine will be 4 length, right? So this is data types are very important to solve the problem of heterogeneous of communication. Also, by specify application-oriented layout of data in memory. So, for instance, the smaller computational grid that we have defined for each process. right? So we can reduce memory to memory copies by avoiding one extra memory copy to the MPI buffers, and also allows us to use special hardware for scatter-getter operation when available. So some hardware provides very fast hardware support for scatter-getter operations. So also MPI derived data type MPI implementation can access to this kind of fast getter-scatter operation. Also, MPI data types are largely used when doing I/O to specify application-oriented layout. So when we will do MPI/O, we will come back to these MPI data types, MPI derived data types. So let's look at non-contiguous data types. So they are provided to the user to allow to avoid extra copy by MPI implementation. So we can define, so in the find of making an extra copy by providing these strided values, what we can do is to define what is the data SS pattern, in this case as strided, avoid this extra copy and send it directly to the network for the communication. So MPI implementation are more or less successful in performance in providing this. Strided copies of basic types likely to be the best when talking about performance. So an MPI data type define a type signature that is an internal representation of the data types. So for instance, if the sender declares a data type consisting of two doubles, and send 4 elements of that type, the receiver can receive it as 2 elements of the type consisting of 4 doubles. A data type signature is defined as a sequence of pairs, basic, type, and offset. So a sequence can be an int at offset 0, followed by another int at offset A, followed by a double at offset 16, and this will be basically defined as this sequence here on the slide. And an MPI data type has a size and an extent that are slightly two different concepts. So the size is the number of bytes of the data types, while the extent controls how a data type is used with the count field in a send and a similar MPI operation. So it's strongly related to where actually MPI send receive started the communication, where to find the data in an MPI send and receive. So what does the extent do? Consider the MPI send with the buffer that we provide, the number of elements that were assigned, and then the data type. So how actually this buff gets sent? So well, MPI defined this as sending the same data as a loop from 1, so from 0 to the number of data type, and we basically send we use this extent function to get access to the data in the data type. So here is basically the starting address of buff. So is basically the counter multiplied by the extent of the data type, right? Where buff is a byte type. So extent is basically used to decide where to send from or where to receive to in MPI receive in a message where we sound more than one of these data type. So we can change the extent. So MPI provides a routine MPI type create resides for changing the extent and the lower bound of the data type. So this doesn't change the size. It just changes how MPI decide what addressing memory to use in offsetting one data type from the other one. Right? The usage is MPI type create resides, old type, lower bound, extend, and new type. So except in a very corner case, lower bound should be set to 0. Let's look at a simple example of sending columns of a matrix. From assume in C, assume that we want to send a column from a matrix with the sign n times m, and we want to send this column. So in scene, the AI call is not adjacent in memory to basically to the next column with index I plus 1. So what can be the solution? Well, one solution, it will be to send each element separately, right? Each element of the column. So we can make a loop, and then we have the index, one index for the column, and then we loop across all the elements of the column, and for each of these elements we make a message, right? So why we don't want to do that? Well, the reason is the performance, right? So we will see later on, each communication includes a cost fix called latency. So it's better to send a long message with all these column elements. So we pay this this fixed cost just once, right? So we just do one send in doing multiple send to avoid this extra this fixed cost called latency. So for performance reasons, we don't want just to send element by element. What we want just to send the whole array with the column. So for doing that, the MPI time vector comes to help us, right? So what it does is we can create a single data type representing elements separated by a constant distance, the stride, in memory. So in this case, we have n items that are all the elements of the column separated by a stride of m. So the stride is coming from the stride of how this access is in memory. So to create a data type, it consists of basically of two operations. First, we define the data type, and we provide how many elements and basically the stride and what is the basic element type. So we use MPI type vector. In this case, we have n elements consisting of our column, and then we have the stride, then MPI double and new type. After we define it, we need to actually commit the new type. So keep in mind that the MPI time commit is required before using a type in any MPI communication operation. So we need not only to use MPI type vector to define it, but also we need to commit it before doing communication. And then we can send one instance of this type. We provide the starting address of our array, and then we basically decide, well, the type is this new type I've been defined here, that is n elements with the stride m, and this will send our column. So how do we send the columns of the matrix? Can we do this where we basically increase the just the count number to 1? We cannot really do this, and the reason is, think about how the extent new type is defined. So extent new type is the distance from the first to last byte of the type, right? So the last byte is a and to the column. So what is the first location of a that is sent after this first row, right? So this is this will results in not in what you want to send. So the solution actually is not to send two of these data types, but actually is to define a different data type, so a new type using MPI type vector, where we included the count here. So we have still n elements. We take 2 and we provide as a count, and then we provide as the stride, right? So this will basically use to send 2 columns, changing the block count in the data type. So the MPI type vectors is for very specific usage. It rarely makes sense to use count other than 1 with the vector type, but in this case, we will use count 2 to send the two columns. So what are the realities about MPI data types? So there are different implementation of MPI. All the different implementation might have different performance using data types. Not all the patterns are well optimized. So some example, so for instance, some cases manual packing is actually faster than MPI data types. So it really depends on the on the case. It does provide a very neat way to have a complex data access pattern to a particularly array. So I wanted to cover it, but some of the implementation, they don't provide the performance that we expect. I didn't cover. I just covered the MPI vector data types to basically give access to stride it. There are others MPI data types that we can construct. So, for instance, MPI type contiguous, MPI index, MPI type struct for creating a structure to be sent. So I just give you a broad overview of MPI data types. Why we might want to use them. We'll provide some more material on how to use some of these MPI data types in application. So this is the last slides in the last of this lecture. In the last lecture, I will give some info. I will introduce MPI topologies, virtual topologies, and how to use in the application. Talk to you soon.